All right, so we're going to take on the first law of thermodynamics, and the first thing we want to look at is what the word thermodynamics means. So let's write it out, because it turns out that the word thermodynamics contains within it very important fundamental relationships. So let's pick off the first part, thermo. Well, this implies thermal, which implies warmth, or more specifically temperature, but it also suggests heat. And as we'll see, heat is profoundly important to the first law of thermodynamics. So that immediately raises the question, well, what about dynamics? Well, dynamics implies flow, and in particular, a flow of heat. But dynamics also implies motion, and motion implies work, because work is by definition, as we know, a force times a distance. But it's the union of heat and of work that together constitute the foundation for the first law of thermodynamics. So the first thing we recognize is that we're looking at the flow of heat and the flow of work, but that means it has to be a definition of a flow through something. And a very important distinction, the first law, is to separate the system from the surroundings. Because if we're going to define the flow, the motion of heat or work, we have to define it carefully through some surface. And that surface, in fact, separates the system from the surroundings. And so we're going to discuss heat, which we represent as Q, and we're going to represent work, which we represent as W. But we're going to look very carefully at the fact that this heat is going to go into or out of the system, as is the work done on or by that system. So this exchange between the system and its surroundings becomes very important. And if you think about what Joule did, the genius of Joule that set the energy scale and defined quantitatively the conservation of energy, as we saw in the past chapter, part of his insight was to say, I'm going to separate the system of these paddles swinging through water that transfers the work that goes into that shaft to rotate those paddles, and he could measure the mechanical energy, or the work, by taking a mass, lowering it through a certain distance, delta H, and he could calculate exactly what that mechanical energy was. But look what he did. He passed that work as a rotating shaft through the intersection between the system, which was the water, metal, and swinging paddles, from the surroundings, which are represented by the falling mass that contributed the energy, into which the rotating paddles converted that mechanical energy to thermal energy. And then he could equate the mass times the acceleration of gravity times the change in height to a proportionality constant times the change in temperature. And that proportionality constant was the heat capacity. But notice, intrinsically, you could draw a border between the system and the surroundings by drawing it right through that equality sign, because the mg delta H represented the surroundings, but the increase in temperature of the system of paddles, steel, and water represented the system. So he beautifully isolated the surroundings from the system, and therefore he could measure exactly what the relationship was between the mechanical energy released by the falling mass and the increase in temperature of the water. So now we respect the fact that we have to very carefully separate the system from the surroundings. And we can also write another important expression, and that is that the change in energy of the universe is simply equal to the change in energy of the system plus the change in energy of the surroundings. And we also saw in the last chapter that when we assign E to the total energy of the universe, the conservation of energy demands that the change in energy of the universe is identically equal to 0. This is the representation of the conservation of energy, and as we saw in the previous chapter, scientific progress was very, very slow until the scientific idea of the conservation of energy defined what energy is. And as soon as it was recognized through the work of Joule in particular that energy is conserved, scientific thought accelerated remarkably rapidly. So now if we use the fact that the change in the energy of the universe equals 0, which represents the conservation of energy, it means immediately that we can write the expression that the change in energy of the system is equal to, but opposite in sign, to the change in energy of the surroundings. The next thing we want to do, based on our experience with this mechanical system that we looked at, so we're going to look inside the system, and the system is going to be comprised of this mass oscillating on a steel rod that strikes a spring at the bottom and rebounds, so it's oscillating back and forth. And we recognize that the energy of the system was equal to the kinetic energy of motion of that ball plus the potential energy, and the kinetic energy and potential energy were traded off against one another. But there was another very important component, and that was the thermal energy of the system. And this would be manifest, for example, if we took a picture in the infrared, that rod that the ball was sliding up and down would glow red in the infrared because of the conversion of mechanical energy to thermal energy. So we want to write the energy of our system as equal to the mechanical energy, that is the sum of kinetic plus potential energy, plus the thermal energy that represents the motion of the molecules. And we recognize immediately that the mechanical energy is macroscopic, but the thermal energy is microscopic. And it's microscopic because it refers explicitly to the motion of molecules, and the velocity of those molecules determines the temperature of that body. But let's pursue our system for just another moment. We know that the energy of this system of the oscillating ball on the rod and the return spring can be represented as our kinetic energy plus the potential energy plus the thermal energy. So the change in energy is equal to the final energy minus the initial energy. But we can write this now as the energy in the mechanical component plus the thermal energy in the final state minus exactly the same variables, the mechanical energy plus the thermal energy initially in the system. So that means that we can allow this ball to oscillate, and it can oscillate until it stops. And when it does that, all of the initial energy is tied up as thermal energy. It's increased the temperature of the entire system. But we can also carry out a thought experiment. We could add a little arm in which, when that ball came to the top of its trajectory, we pulled up on the rod to add kinetic energy downward to make up for the energy that is converted to thermal energy. That is, we could do external work on this system, and that would be equal to the force times the distance each time we injected mechanical energy into the system through this rod. That means that if we're going to maintain the kinetic energy, it means that the change in energy of the system is exactly equal to the work that we've done externally on the system through that little rod. And that means because of the inexorable conversion of mechanical energy to heat, we can write the fact that the change in thermal energy is exactly equal to the work done externally by that small rod. So this thought experiment then is very helpful in linking mechanical energy with thermal energy. So when we come back to our assembled system, we recognize that the kinetic energy and potential energy are exchanged, because as the ball rises, the kinetic energy disappears, but the potential energy increases until it reaches the top of the throw, accelerates back down, and kinetic energy and potential energy are exchanged. But they're also, through the friction between the ball and the rod, contributing to the increase in the temperature of that rod, which is manifest as the thermal energy in our relationship. So the energy of the system, the kinetic energy plus potential energy plus thermal energy, is then represented as the sum of simply the mechanical energy and the thermal energy. But now we're ready for an important definition. When we look at the work, we're going to define the work done externally as greater than zero when work is done on the system. When work is done by the system, we define this as work being less than zero. So the external work is less than zero when the system is doing work on the surroundings. External work is greater than zero when the surroundings are doing work on the system. And finally, we can write then that our change in the energy of the system, which is the sum of the mechanical and thermal energy, is exactly equal to the work done externally by the system or on the system.